Hello, I'm Glenn Cowan from Concordia University. In this video, we will look at the physical structure of MOSFETs in order to explore the capacitive effects arising in CMOS devices. We will review Miller's theorem and apply it to a common source amplifier, allowing us to compare the effects of the various MOSFET capacitors. Finally, we will look at and compare the gain bandwidth product of common source amplifier to the NMOS transistor's transition frequency, or FT. Let's get started. Here we have a MOSFET that's going to capture the DC or low frequency IV behavior of the MOSFET, along with all the different capacitive effects wrapped around it. So capacitors are going to limit the speed of the circuits that we're going to build with MOSFET. So here we've got gate to drain, drain to body, source to body, gate to source, and gate to body. And all these capacitors are arising from various depletion regions, charge distributions, and fringing effects. This slide shows a summary of the relevant capacitors for a MOSFET when biased in strong inversion. Okay, so let's take a look at these in a bit more detail. For CGS and CGD, in triode, or deep triode in particular, they're the same. We've got an area capacitance formed by COX, W, and L, and it's split between the gate to source and gate to drain. When we move into saturation, only the source supplies the charges to the other side of the capacitor, and so CGS is going to be the only major gate capacitance. We're going to have a CGS of 2/3 COX W times L, and then the gate to drain capacitance is going to be due to overlap capacitance only, so not due to the inversion charge. However, in saturation, even though CGD is just overlap capacitance, it could still be about 1/3 the value of CGS. And we'll see later in these slides that being only 1/3 because of something called the Miller effect, CGD may be just as detrimental to the bandwidth of a circuit as the gate source capacitance. And then if we look at the drain to body and source to body capacitances, these are junction capacitances. Junction meaning PN junctions. Now, we can play some tricks to reduce these by maybe a factor of 2, and we'll look at those later. They're also voltage dependent, and these are all the equations here for the voltage dependency. Having said that, I've never seen a circuit that was designed where the driver was the DC node voltages in order to reduce these capacitances. These are the equations for depletion capacitances, and we basically have to live with them. The only thing that we do have control over is the area. So the area of the entire PN junction is a parameter of the capacitance, and we may be able to play some tricks to reduce it. Now, all of the capacitors that we've indicated here, at least the first 4, are going to scale with width. Some of the gate to body overlap at the ends of the gate won't scale with width, but the major capacitances scale with width, and then CGS is also proportional to the length of the transistor. Okay, let's look at these diode capacitances in a bit more detail. So this shows the cross-sectional view of a MOSFET, where we've got the source and the drain, which are N plus in an NMOS, and the P minus substrate. So this forms a PN junction, and in general, it's reverse biased. There might be 0 volts across it, but even when there's 0 volts across it, there's still a depletion region. Okay, so let's take a look at one of these in more detail. So just looking at that junction, we've got a diode. Now let's look at the 3D structure of it. So looking from the side, we see this view. Looking from the top, we see this view. So the red is the gate, and this dimension here is the width, and this dimension here we're calling x. In 3D, we're going to have width, x, and this distance d, which is the height on the surface of the wafer. Now, as a circuit designer, we don't have control over d and x. We're going to use the minimum x whenever we can, and beyond that, we can't make it any smaller than some minimum. And d, we certainly don't have control over as a circuit designer. We do have some control over width, so let's see what we can do to try and minimize the effect of the width of the transistor. Okay, so here's a layout of a single transistor. So we haven't drawn the substrate connection. Don't forget to include those in a real layout. The actual colors here will vary from technology to technology, but we've got here the green, which forms the source and drain regions of the transistor, the red, polysilicon, forming the gate, and we've got contacts from metal 1 down to the drain, metal 1 down to the source, and then we're going from, say, a metal 2 down to a metal 1 down to the gate here. So this is the layout for a transistor of width W, length L. Okay, let's split this device into fingers. So we're going to start with a transistor of width W, length L. And we're going to split it into two transistors, each of width W over 2, and the same length. Now notice here we've connected the drains of both of them together, the sources of both of them together, and the gates of both of them together. So in the schematic, we draw it like this. Now remember from the review of the IV characteristics that all of the expressions for current were proportional to width. And that proportionality to width is going to be true whether or not it's a nanometer transistor or a much larger feature size transistor. We might get some narrow channel effects when width gets close to the minimum, but for any non-minimum width transistor, current is proportional to width. Okay, so we haven't really done anything special here. We've just got these two transistors in parallel. We can, of course, extend this to dividing it not into two fingers, but dividing it into n fingers. Okay, so we could draw this width length transistor like this. So I've rotated around the device that was down here at the bottom. Now, why would we want to do that? Well, there's a couple good reasons. The first is related to gate resistance. So this polysilicon is not that conductive. It's not as conductive as the metal. And when you think of it this way, if we have some capacitance from gate to source, we have to charge up that capacitance. So we're going to have current flowing laterally in this gate. The longer the gate is, the more resistance between here and that far end of the gate. If we split it into two, the maximum length which current must flow is cut in half. So there's an R divided by 2. We've also put these two R over 2s in parallel. And so there's a net reduction in effective gate resistance by 4 when we do this. Now, in both of these layouts, we could contact the gate from both sides, and we could route current to the far side through a much more conductive metal. Nevertheless, splitting into two fingers would reduce the gate resistance by a factor of 4. Another reason why we would do this is that we can now play tricks with this common drain node. So we've got these two transistors, both of width W, length L, shown here. Here I've drawn them with two drain diffusions. So this transistor would have the same total capacitance as if we laid it out in one finger with a width of W times 2. But now we can push on both sides and mush it together and merge the drain diffusions into one drain diffusion. So now the drain current is going to come down here. Part of it's going to flow this way through a transistor of width W. Part of it's going to flow this way through a transistor of width W. The overall effective width of this structure is 2W. So we've got the current conducting capability of a transistor of 2W with the drain capacitance approximately the same as a transistor of width W. So in general, we're going to split transistors into fingers. If we split a large transistor into a large number of fingers, we'll end up sharing source diffusions as well. So we might have one, in general, we're going to have one more source diffusions than drain diffusions when we split a transistor into an even number of fingers, assuming that we assign the drain node to the node with fewer diffusions. Okay, let's summarize a little bit of this capacitance material. So the CDB can be almost as big as CGS, depending on the layout. If we do these tricks, it might be a little bit smaller, but we can't ignore it. Of course, in an SOI technology, the transistors are sitting up on an insulating layer, and so CDB is much smaller. In general, these capacitive effects can be taken into account in good schematic models. So oftentimes, in the schematic, we can specify the number of fingers and how the source and drain areas are shared. The model will account for gate overlap capacitance from the polysilicon gate down to the surface of the diffusion area. But the model, the intrinsic schematic model, may not account for the overlap or the fringing between the metal that's on top of the source and drain and the polysilicon gate. So it's really important to do post-layout simulation on any layout to get all the capacitive effects out. And CGD is a key capacitance in structures such as the common source amplifier that we'll see in more detail in a minute, and it can also limit the performance of some of the more advanced structures like active inductor circuits. Okay, let's take a look at Miller's theorem. This shows an amplifier. It's an inverting amplifier. The gain is minus A. Here, we're assuming that this number A is positive. It's greater than 0. So overall, we have an inverting amplifier. So the output voltage V2 is minus A times the input voltage V1. We have currents flowing in and out of that admittance. Now, of course, this admittance, as a two-terminal admittance, these two currents are going to be equal and opposite, but let's leave them as these independent variables for now. Miller's theorem is a trick that will let us split this feedback admittance into an input and output admittance, as shown here. So instead of there being one feedback admittance Y, we have an input admittance Y1 and an output admittance Y2. Again, I've labeled these currents as separate as being I1 and I2. So we will come up with equivalences for Y1 and Y2 by matching the currents I1 and I2 in the two schematics. So on the left, I1 is going to be the voltage drop across the admittance multiplied by the admittance. So V1 minus V2 multiplied by Y will give us the current I1. Now, we're going to substitute in for V2. V2 is minus A times V1. So we get V1 minus A times V1. On the right, I1 is going to be equal to V1 times Y1 because this is a grounded admittance. For I2, we're going to do the same thing. I2 is V2 minus V1 times Y. And then we're going to substitute in V1 being equal to minus V2 over A. And that's going to be equal to V2 times Y2. Okay, so then when we factor these things out and then make the equation here, equating the left and right side of these last two terms, we can get Y1 is equal to Y times 1 plus A, and Y2 is equal to Y times 1 plus 1 over A. So the significant thing here is that if we have a large gain, if A is a big number, then the equivalent admittance is much bigger. And so this admittance could be a real admittance like a resistor, or it could be an imaginary admittance like a capacitor, or it could be some combination of real and imaginary. Let's apply this notion to a common source amplifier. So let's ask ourselves, which capacitor has more of an effect on the bandwidth or on the input impedance of this circuit, CGS or CGD? Well, let's split CGD into an input and output cap. To do this, we're going to write the small signal model. So I've drawn the small signal model here with CGS, CGD, the voltage-controlled voltage source, and I've voltage-controlled current source, pardon me, and I've ignored RO. We could lump it in here as being simply in parallel with R. So CGD is the Y, the admittance from the earlier slide. So to split it, we need the gain A of the inverting circuit. Now remember, A, the overall gain of the amplifier is minus A. So the overall low frequency gain of common source amplifier is minus GM times R, and so A is just GM times R. And we're going to use the low frequency gain, and this is going to help us to ultimately predict the onset of when these capacitors matter. Okay, so we're going to split it into capacitor C1 and capacitor C2. And we will do this by scaling up the admittance. So we know that when we apply Miller's theorem, the admittance of C1, or of Y1, is going to be the admittance of Y times 1 plus A. So I did a little bit of a trick here, and I guess maybe we should comment on that, that really what Miller's theorem did is it told us that Y1 was equal to Y times 1 plus A. Now, of course, the admittance of a capacitor is simply J omega C1 in the case of Y1, and J omega CGD in the case of Y. So that's what it would be from sort of first principles, but we can then cross out the J omega, because it's common to both sides, and say, okay, C1 is equal to CGD times 1 plus A. Likewise, we can look at C2. So C2 is going to be CGD times 1 plus 1 over A. So now C1 and CGS are in parallel. And we can see that if we assume that CGD is about 30% or so of CGS, for any value of A greater than 2, this CGD times 1 plus A is going to be equal to or greater than CGS. And so we can say, for the common source amplifier, CGD is the dominant source of input capacitance. Okay, let's look at some overall technology limitations. So right now, CMOS is the dominant technology choice for applications that require high speed and high integration. If all we care about is high speed, then there's some silicon germanium technologies that are going to find application in certain high-speed applications. In general, what we see, though, is that whatever SiGe can do today, CMOS can do in a few years. So in terms of CMOS circuits and CMOS technology limitations, it's reasonable to ask yourself, how fast can circuits operate? So if you're given a design challenge and you're given a technology, it's really great to be able to say, yes, that's possible, or no, that's not, or it's possible, but it will be really hard. So when you're given a technology, oftentimes there's some general numbers that will be thrown around, like FT, or gain bandwidth product. So I think we want to take a look in a little more detail at what is FT, and how does that relate to the gain bandwidth product of circuits. So for CMOS, there's a rule of thumb that says that the FT, or transition frequency, is 10 terahertz nanometers divided by L-min. And we're going to express L-min in nanometers. So for example, in 45 nanometer, we might have an FT of around 200 and change gigahertz. So what does that mean, though? Does that mean we can get circuits that can do useful things at 222 gigahertz? Well, let's take a look. So the definition of FT, well, it's the frequency at which the magnitude of the AC gate current is equal to the magnitude of the AC drain current. So down here, we've got a single transistor, and we've biased it with a DC source. And the input is going to have a combination of AC and DC. So a DC will give it the bias, and an AC will give it the signal. So the gate current phasor is going to be VGS multiplied by the admittance, omega C. And the total admittance, looking this way, is going to be the sum of CGS and CGD. We don't have any Miller effect here because the voltage gain from here to here is 0. We're connecting the output to a DC source. Now, the DC current, or pardon me, the drain current phasor is simply VGS times GM. You can draw the small signal model if you're a little rusty with this. For this work, we're going to ignore the fact that the drain current phasor has a component of it that comes from the gate drain capacitance. Okay, so we're going to equate these two. VGS is equal to omega t times C. So the frequency at which they're the same is omega t. So we put an omega t here, C, and then VGS times GM. So we get rid of the VGS, we rearrange, and we get omega t is equal to GM over C. So that's a common thing that we'll see, frequencies written as a conductance over a capacitor. Okay, let's look at the gain bandwidth product. So this slide shows a common source amplifier, and for now we've just said there's some total capacitance at this node. So we expect some sort of frequency response that looks like this, where we have some low frequency gain that we've already looked at how to calculate, some sort of pole frequency here, a bandwidth, and then a 20 dB per decade slope. So this circuit is a first order circuit, and so we're expecting this to be a slope of minus 20 dB per decade. That's the same as saying the frequency dependent gain out here is inversely proportionate to the frequency. And this is the voltage gain of this circuit. So the gain bandwidth product can be found by multiplying the bandwidth times the gain. So the unity gain frequency, FU, is equal to F bandwidth times the DC gain. And the DC gain, or at least the magnitude of the DC gain, is equal to GM times R. And the bandwidth is 1 over RC. You could get this by writing a KCL in the S domain at this node, and that's something we'll review in another set of slides. So the gain bandwidth product, omega U, DC gain times bandwidth. GM times R over 1 over R C out. The R's cancel, and we're left with GM over a C. Okay? So we have a very similar form for the gain bandwidth product and the transition frequency. But, so the numerators are the same, it's both a GM, but the denominators, these C's, are going to be different. In this case, the C is a big mess. It's all these capacitors here. So we have the drain to body capacitance of transistor M1, maybe some wiring capacitance, CGS of the second transistor, the Miller effect on the second transistor, and then a little bit of bonus from the CGD that's hanging onto this node here. So that capacitance is going to be about twice as big or more, depending on what this wiring capacitance is, as just a CGS. And that's assuming that both of these transistors are about the same size. So let's compare these. So in units of hertz, we've got GM over 2 pi C out for the unity gain frequency, and GM over 2 pi C. So we already said C out is going to be greater than C by at least 2x. So that'll mean that the unity gain frequency is less than half of this transition frequency, the number that's thrown around when you hear about a technology. So that means that to get a gain of 2 at, say, 40 gigahertz requires a unity gain frequency of at least 80 gigahertz, which in turn would require an FT of greater than 160 gigahertz. Another side note here, though, is that FT is typically measured with the most GM you can get from a transistor. So what would that mean? That would mean the largest VGS possible, the full supply giving VGS. But real circuits usually have other things in the stack between VDD and ground, meaning that this GM here, is going to be less than the GM over here. We can also look at FT in terms of technology parameters. So for GM, we'll assume a square law model, and we'll write mu n Cox W over L VGS minus VT. And for C, we'll just assume it's the gate source capacitance. If we substitute these two expressions in for FT, we can reduce it to having this relationship. We have VGS minus VT in the numerator and L squared in the denominator. This shows us two things. It shows us the speed power supply voltage trade-off, meaning that the more voltage we allocate to the gain transistor, the more speed we can get. And also, of course, the fact that reduced feature size technologies are going to give us a higher FT. Thanks for tuning in. If you have any questions, comments, suggestions for future videos, please don't hesitate to send me an email at gcowan@ece.concordia.ca. Thanks for paying attention.